Put them on here. You only need 1 gram anyway. Anything else is ground, man. And everything's over here. You just put that yellow tape. You're clear. We need to loosen up these balls.
Watch out.
Wait back.
Hold on. Watch yourself.
Great, other way. Stop. Put a couple nuts on these things. I think we're good, actually. Just put a couple.
It's going to be a few minutes. It's going to be a few minutes if you want to stretch your legs. I'll sit up here for a few minutes.
Man, it's loud.
The bottom guys are going to hold in. All the way up. Very nice. One more too. got this. We need to make sure that we're aligned. You're lined up. You gotta look.
micro.
So he went ahead and logged another whole book. He just voided out all of his stuff the other.
Avoided everything. That's a big job.
I know.
You have to avoid these three, and then skip, then avoid these.
You guys ready to come out? kicking the nozzles pointing right at it right now. Let's cover the deck before we get on the deck. Just go back to where I'm in that tree. Bolts up there because I knew we were at the right height.
Good afternoon. My name is Dwayne Brown with the Office of Public Affairs, and welcome to NASA headquarters. Today, you will hear about the science and mission objectives of an extraordinary mission. New Horizons is the first scientific venture to distant Pluto and its moon, Charon. It is also a mission of many firsts and many years of hard work. We will have brief presentations from our presenters. We will then open it up for questions here at NASA headquarters and then move on to our phone lines and NASA centers across the country. A brief note before we start, the launch of New Horizons has been rescheduled from January 11th to January 17th with an extended launch window of February 14th. This is to allow processing and inspection of the launch vehicle. Introduce you to our panelists for today. Andy Dantzler, Director, Solar System Division, NASA headquarters. Dr. Alan Stern, New Horizons Principal Investigator, Southwest Research Institute, Boulder, Colorado. Bill Gibson, New Horizons Science Payload Manager, Southwest Research Institute, San Antonio. David Kuchnikevich, New Horizons Mission Systems Engineer, Johns Hopkins University, Applied Physics Laboratory in Laurel, Maryland. And Glenn Fountain, New Horizons Project Manager, Johns Hopkins University, Applied Physics Laboratory. And we'll kick it off with Andy.
Thanks, Dwayne. The vision for space exploration, as outlined by the President, calls for continued robotic exploration of our solar system. Over the past 40 years, NASA has sent spacecraft to many objects in the solar system, including all of the major planets except one. Now, with this mission, New Horizons, we're setting our sights on Pluto. New Horizons is the first in a new class of planetary exploration missions that we call the New Frontiers missions. New Frontiers lies in that intermediate ground between the smaller missions like Deep Impact and the larger flagship missions like Cassini. And New Horizons also has many other firsts, if I could have the first slide. New Horizons is, of course, the first mission to Pluto, but it's also the first launch since 1977 to an unexplored planet. It's the first mission to explore a double planet, the Pluto-Charon system. And if all goes well, it'll be the first mission to continue on to study Kuiper Belt objects. Also, if we have the next slide, you see it is the first mission led by a PI-led mission to the outer planets. It's the first planetary mission to carry an instrument entirely built by students. It's the first mission to the outer planets led by the Johns Hopkins Applied Physics Laboratory and Southwest Research Institute. And when launched, its speed will make it the fastest space mission ever launched. And we'll get into that a little more later. But why go to Pluto? Just think about Pluto. raises images of something very dark and far away and cold. But actually, Pluto is a treasure trove of scientific discoveries just waiting to be uncovered. It's different from the inner rocky planets. It's different from the outer gaseous planets. And as such, it holds many clues as to how the solar system was formed, and also perhaps how other systems are formed. So we're looking forward to a successful New Horizons launch, a successful New Horizons mission to help us explain to help us meet one of our key objectives of understanding the formation and evolution of our solar system. Alan?
Thanks, Andy. Well, if I can have the first graphic. It's been a long road to get here, and we're now just 1 month from launching from Launch Complex 41 down at Kennedy Space Center in Florida, the first mission to the Kuiper Belt and the Pluto-Charon system. This is, in a very real sense, the capstone of the initial reconnaissance of the planets that the United States has led for the world since the 1960s. As Andy said, we're going farther to reach our target, and we're traveling faster than any spacecraft ever has. And this is a little bit about leadership. This is a little bit about rewriting the textbooks about the outer planets. But I also want to point out it's also about inspiring the next generation of scientists and explorers that we hope will take us to even greater heights. If I can have the second graphic in the presentation. I'm going to show you a little bit about our route of flight to the Kuiper Belt. Now, this graphic is deceiving because the scale is enormous. The Earth's orbit can't even be seen on this graphic. In fact, the innermost white circle is the orbit of Jupiter, 5 times as far from the Sun as the Earth is. Our route of flight is indicated by that red trajectory line, the spacecraft path, from Earth to Jupiter for a gravity assist, and then a long coast out across the outer planets, Saturn, Uranus, and Neptune, to meet the orbit of Pluto, the yellow line on this graphic, as it crosses the plane of the planets. Pluto, of course, is embedded in the Kuiper Belt, the largest structure in our planetary system, dotted with almost 500,000 worlds and worldlets that are 4 billion years old. In a real sense, this is not just the journey 4 billion miles away, but also 4 billion miles back in time. And it's really no wonder, because of the value of this ancient structure to our understanding of the origin of the solar system, that the National Academy ranked this mission #1 in the runway for a new start in this decade among medium-sized planetary missions like New Horizons. All right, next chart. Well, meet Pluto and Charon. Very unusual pair of worlds. The first binary planet system we have ever explored, and the first ice dwarf, a whole new class of planets, as Andy alluded to. And you know, whereas we know of 4 terrestrial planets and 4 gas giants, we expect that there are hundreds, if not thousands, of these ice dwarfs. And so this class of planet, which we have not yet reconnoitered, is in reality the most populous class of planetary body in our solar system. And that's what this mission is about, is to study a binary planet for the first time, to make the first reconnaissance of ice dwarf bodies, and some of the other attributes of the Pluto system that make it interesting. It's a scientific wonderland for atmospheric scientists. Its atmosphere is escaping like a comet, but on a planetary scale. Its surface, which is only 40 degrees above absolute zero, is covered in exotic ices. It has strong seasonal and global change effects that we already know are taking place. So if I can have the next slide, I have to say you can see why we think it's going to be like kids in a candy shop when we arrive at a system like this. You know, it just keeps getting better. As we study the Pluto-Charon system, we keep being surprised. Even from Earth, as difficult as it is to study the Pluto system, which is 10,000 times fainter than the eye can see, 100 times smaller than Mars as seen from the Earth, and yet we're still able to make some discoveries. In 2001, we discovered that binary objects litter the Kuiper Belt. That Pluto is not alone in this respect, but it's in fact an archetype. In 2002, we discovered that Pluto's atmosphere is undergoing rapid and dramatic global change. And as this graphic shows you, in 2005, just this summer, we discovered that Pluto and Charon are more than we thought. It's not a binary system alone, but in fact a quadruple, with at least 2 more satellites, perhaps more still to be found, either by Hubble or perhaps by New Horizons. So hold on to your hats. we think 2015, when we arrive at Pluto, is going to be very exciting. I want to bring up the next slide and just provide one word of caution. The best image ever taken of Pluto is shown on the left in this graphic. It's taken by the Hubble Space Telescope. You can see how crude that image is. We can barely discern that Pluto's northern hemisphere is brighter than its southern hemisphere. Perhaps that's evidence of a large ice cap. Perhaps not. In the center, you see another object at similar resolution. It's the Earth's moon, shown on the right. And you can see that when we have very low resolution, the only thing that's available to us for Pluto presently, it's very hard to make the correct interpretation. In fact, it's very likely that one would misinterpret. In fact, this is really the lesson of planetary exploration. Our Earth-based observations are often too crude to really tell us the true nature of these systems. If you think back across the 50 years, 40 years of planetary exploration, you remember that no one really expected river valleys on Mars or Mercury to be a planet that's almost all core. We didn't expect volcanoes in the outer solar system, and the list goes on and on. We have been wrong again and again by underestimating nature. Our chance with New Horizons is to take a peek at the last kind of body, to see if we can get the last one right. Whether we're right or whether we're wrong, we expect to learn a lot. I'll take the last graphic. Well, this is an old stamp from 1990, and you can tell from the price of that stamp. The U.S. Post Office commissioned a set of stamps in honor of the U.S. leading the exploration of the planets. Of course, when it got to Pluto, it couldn't mention a Mariner mission or a Voyager mission or a Pioneer mission. This is what the stamp said: not yet explored. Well, we aim to change that. Perhaps we aim to change that stamp as well. Our goal is to arrive at Pluto in 2015. In fact, our planned arrival date, by cosmic coincidence, will be on the 50th anniversary of the first flyby of Mars by Mariner 4. The kind of thing that we're doing with New Horizons and with this kind of planetary exploration leaves a lasting legacy from our time and from our nation. It's a chance to, as I said earlier, inspire future generations and leave a legacy for all humankind. Bill?
Very good. Thanks, Alan. If I can have the first graphic, I'll introduce you to the New Horizons science payload. The payload consists of 7 instruments. 3 of those instruments are cameras, the Lori, Ralph, and Alice cameras you see here. There are 2 plasma analyzers, Pepsi and SWAP. There's a radio science instrument, REX, that's actually integrated with the spacecraft telecom system. And then there's the student dust counter. If I can have the next slide, please. I'll introduce you to the Ralph instrument. By the way, Ralph is not an acronym. It's named affectionately after Ralph Cramden of the TV series The Honeymooners. Ralph is a combination visible and infrared camera. In the visible mode, we can do both black and white as well as color images. At closest approach, Ralph will give us resolution of about 1.5 kilometers in the color bands and about 0.5 kilometers in the black and white. The infrared camera portion of Ralph will give us surface composition and temperature with a resolution of about 7 kilometers. In addition to its role as a science instrument, the Ralph instrument also doubles as part of the navigation system. Ralph's black and white starfield images are used by the nav team to help us find our way to Pluto. The Ralph instrument was developed under the leadership of P.I. Stern. The telescope and the visible camera were developed by Ball Aerospace. The infrared was developed by Goddard, and the control electronics and software developed by Southwest Research Institute. If I can have the next slide, please. Let me introduce you to Lori, our long-range reconnaissance imager. Lori is a very high-resolution black and white camera. At closest approach, Lori will give us about 25 meters resolution. Lori will also be the first instrument to give us detailed images of the planet about 3 months from closest approach. And Lori will also be used to take images of the newly discovered moons that Alan made reference to earlier. Lori was built at APL, Johns Hopkins Applied Physics Lab, under the leadership of Dr. Andy Ching. If I could have the next slide, please. This is Alice, our ultraviolet spectrograph. ALICE is used to give us atmospheric composition and pressure temperature structure of the Pluto atmosphere. ALICE was also developed under the leadership of Alan Stern with significant support from Dr. Dave Slater at Southwest Research Institute. By the way, there is another version of this same instrument aboard the European Rosetta spacecraft on its way to rendezvous with the comet. If we could take a look at the next slide, I'll introduce you to the first of our plasma instruments. This is SWAP, Solar Wind Around Pluto. SWAP is a very sensitive, low-energy plasma analyzer that will be able to tell us when we're first encountering the point at which the solar wind begins to collide with the escaping atmosphere of Pluto. SWAP was developed under the leadership of Dr. Dave McComas at Southwest Research. If we can have the next slide, please. This is PEPSI, the Pluto Energetic Particle Spectrometer Science Investigation. PEPSI is a time-of-flight mass spectrometer that can give us atmospheric composition of ions, electrons, and molecular ions. It was developed under the leadership of Dr. Ralph McNutt at the Applied Physics Lab. Go to the next slide, please. The radio science experiment works by measuring the refraction of radio waves as they pass through the atmosphere of Pluto. And from that, we can derive temperature and pressure profiles of the atmosphere. REX can also operate in a radiometer mode, giving us surface temperatures of the planet. The REX hardware was developed at Stanford University under the leadership of Dr. Lynn Tyler and Dr. Ivan Linscott. The telecom system, of course, was developed by APL. Let's go on to our last instrument, the Student Dust Counter. The Student Dust Counter was developed, as Alan mentioned earlier, entirely by students at the University of Colorado. It's used to measure cosmic dust energy and counts. It's the only instrument to operate continuously through the cruise phase of the mission. The project, the scientific leadership for the Student Dust Counter was provided by Dr. Mihail Harani at Colorado University. The original student project manager was Ms. Tiffany Finley, who's graduated and gone on to work in industry. She was followed by Ms. Elizabeth Grogan, who is serving now as project manager for the Student Dust Counter. The New Horizons payload, in summary, is the most compact, low-power, high-performance payload yet to fly on a U.S. planetary mission for a first reconnaissance flyby. Thanks very much. Dave?
Thanks, Bill. I'd like to give you a brief description of the New Horizons spacecraft itself. In addition to a couple of the instruments that Bill told you were built at APL, we also designed and integrated the spacecraft itself starting about 2.5 years ago with the fabrication of many of the components on the spacecraft. And about 6 months ago, we started integrating these components, building up the spacecraft and putting it through its test program. Of course, the spacecraft now is at the Kennedy Space Center, anxiously awaiting launch. If I could have the first slide, please. The New Horizons spacecraft itself is relatively small compared to the spacecraft that we've used recently to explore the outer planets. It will weigh a little bit over 1,000 pounds at launch with a full fuel load of about 170 pounds. The spacecraft is highly redundant. Most of the components on the spacecraft either have physical or functional backups. Our solid-state recorders, of which we have 2, each have the ability to contain about 64 gigabits of information. This is where we'll store the science data during the Pluto flyby and play it back over a period of months afterwards. If I could have the next slide, please. All the electronics on the spacecraft operate on less power than 2 100-watt light bulbs. The electrical power, of course, is provided by the nuclear power source, which we carry. That is one of the components which does not have a backup. These are highly reliable devices which have many years of experience in space flight. In order to minimize the electrical power that's needed to help keep the spacecraft at the proper operating temperatures for the electronics, we have constructed the spacecraft sort of like a thermos bottle, and we try to control the heat that escapes from it. In this way, we maintain the proper temperature environment inside the spacecraft throughout its long mission to Pluto and beyond. And the thermal environment doesn't change a whole lot. It stays more or less pretty close to room temperature. The spacecraft will be put to sleep into a hibernation mode with very few subsystems active after we complete the Jupiter Gravity Assist. This will conserve some of the useful operating lifetime of the electronics. although we do keep the student dust counter that Bill mentioned powered during this portion of the mission in order to help characterize the interplanetary dust environment. The spacecraft will feature what we call a beacon mode. This will be the first operational use of such a beacon mode to broadcast the status of the spacecraft and its health back to Earth. We will listen to this beacon about once a week during the period from Jupiter to Pluto in order to make sure that the spacecraft is healthy. If any remedial action is taken, the beacon will indicate the necessity for that and we'll respond accordingly. I have a short video that shows the spacecraft down at the Kennedy Space Center. In place of the actual the nuclear power source on the spacecraft, there is one of the simulators that we used in the test campaign. You'll notice the large high-gain dish antenna on the top of the spacecraft, which measures 6.5 feet in diameter. The spacecraft is about 7 feet tall from the base to the top of the antenna, and it measures about 10 feet from the tip of the RTG back to the base of the spacecraft. So to describe the mission now, Glenn Fountain.
Thanks, Gooch. Because we have such a long way to go, we put this small spacecraft on one of the largest rockets the U.S. has in its inventory, the Atlas V. The journey begins at the Kennedy Space Center on January 17th at 1:24 p.m. Eastern Standard Time. We have about a 2-hour window each day to get the spacecraft on its way. The launch carries us out over the Atlantic, and by the time we are over the Indian Ocean, we've acquired enough velocity to send us on our way, on its trajectory to Pluto. We have a video clip, if I could have that now. This video clip shows the spacecraft separating from the launch vehicle some 47 minutes after liftoff. We'll get first contact some 3 minutes later from a station in Australia. Leaving Earth, the New Horizons will be traveling at 8 miles per second. At 8 hours later, the spacecraft will pass the orbit of the Moon. Remember that the Apollo astronauts took some 3 days to cover that distance. That comparison gives you some idea of the speed at which we'll be traveling. We launch no later than the 28th of January. Spacecraft encounters Jupiter in February of '07. We plan to use Jupiter Encounter to test out the way we'll be doing the encounter at Pluto. It will be our practice shot for Pluto. We'll also gain an extra 2.5 miles per second of additional velocity as we go forward into Pluto. It yet takes 8 years, 8.5 years addition to get there. We'll be starting to do the imaging of Pluto, and 90 days out we'll be getting our first images better than Pluto. We'll be using the LoRa imaging system to do that, which will give us images 10,000 times better at closest approach than the Hubble Space Telescope. The instruments provide the ability to gather the data, as you heard from Bill Gibson. We'll be making measurements of both Pluto and Charon as we go through the system. And then, after we leave Pluto, we'll be going out into the Kuiper Belt. Going through the Kuiper Belt and out beyond the Kuiper Belt, out of the solar system, and into interstellar space. So that's the journey that we'll be following in the next 10 years.
Okay, we are going to now open it up for questions. We're going to start here in Washington. Please give your name and affiliation. And
yeah, Robert Boyd from Knight Ridder. Can you describe any more what you hope to see or do in the Kuiper Belt? Alan?
Sure. Our objective in the Kuiper Belt part of the mission, I should point out, is formally the extended mission. And its approval depends upon the health of the spacecraft and a decision about funding for that will be made at approximately the time of the Pluto encounter. But our objective is to reconnoiter 1 or perhaps 2 additional Kuiper Belt objects. Let me give you, though, a little bit of a better feel for that. The Kuiper Belt is this enormous structure I spoke about, 5 billion kilometers from here to there, ringing the solar system, dotted with 500,000 small worlds and worldlets, objects as large as Pluto and as small as comets, in fact. The distances between the individual objects in the Kuiper Belt are very great. So a few weeks after the Pluto encounter, when we've chosen our target, we'll fire the engines of the spacecraft. But we'll have to fly distance, something like from here to the sun or twice that far, to reach these Kuiper Belt objects. So it'll take a period of a couple of years after Pluto to reach the first so-called KBO. And then if the spacecraft's still in good health, and NASA agrees, we'll go on to make a second Kuiper Belt encounter, if we have the fuel to do that, in the years following that. Then we'll pass out of the Kuiper Belt region, and there won't be an opportunity for additional flybys after that.
You haven't picked those potential targets like Xena or DW, something like that. It's too soon.
That's right. We'll know a lot more in 10 years. We'll be able to make a better choice.
Frank Roylance from the Baltimore Sun. Given the very high speed that you're going to be traveling, how can we compare the length of this mission with previous planetary missions that went at slower speeds? Is this the longest in duration that we've flown to a planet?
So the Cassini mission took 7 years. So, yeah, this is the longest in duration from Earth to target. That's right. It gives you an idea of how far Pluto is moving at that speed. It will take 9 years to get there.
You all expect to be on the job in 2015 when this planet pull this off?
I'll raise my hand.
Yeah. Yes.
Yes, we'll all be there.
Any other questions here before we go on the network? Okay, I believe we're going to take Kennedy now. Kennedy Space Center, go ahead.
More details about the state of the Atlas V testing and your confidence in the January 17th launch date.
Could you repeat the question? We missed the first part, please. And give your name and affiliation.
Sure. It's Chris Kreidler from Florida Today. And I wondered if you had any more details about the state of the Atlas V testing and your confidence in the January 17th launch date.
First of all, we have a 35-day launch window. We have till February 14th. One of the advantages of having a launch window that big is it gives us several opportunities to get off the Earth. Lockheed Martin and KSC personnel are looking into the state of the launch vehicle, doing continuing tests, and making sure it's perfectly safe to launch. We're being prudent and taking all measures to make sure it's ready, and we won't launch until it is.
Okay, I believe we're going to now switch to CBS News.
Bill Harwood. Bill Harwood, can you hear me?
Go ahead, Bill, we hear you.
Yeah, thanks. Two quick ones from me. I was wondering, okay, thanks. Was looking for a breakdown on fuel usage, how much it takes you to get there, and how much will be available after the flyby if your predictions all hold up for use to go after a KBO. That's number one, then I have a follow if I can.
I'll take a crack at that. Bill, we have 77 kilos of fuel on board, and we don't need to use any of that fuel to boost us to Pluto. We use all of the fuel for spacecraft pointing maneuvers and for trajectory trim corrections. So if we get off to an on-target launch and we don't have to make an initial mid-course correction of any real size, we'll have a lot of fuel when we reach the Kuiper Belt. Over half the tank will be full. Even in our more conservative predictions, we expect that about a third of the hydrazine will remain after we pass Pluto and be available for the extended mission in the Kuiper Belt.
Bill, you got a follow-up?
Was wondering what the total useful life of the RTG is, assuming, I'm sorry, I'm getting feedback over the phone, so I'm trying to do this again. Total life of RTG over the life of this program. In other words, when you think your power levels will drop below the point where you can operate your instruments is the first part of that second question. And the second part of the second question, if you miss this window, would you review once more time what happens to you guys if you don't get off this year? Thanks a lot. Sorry for all the confusion.
Yeah. The RTG has the power producing capability to extend this mission out for at least 10 years beyond the planned Pluto encounter. After that, we can take additional measures on board the spacecraft to operate with fewer components on and probably extend that life even further. So the RTG output power is really not a limiting factor in the main mission to Pluto or the extended mission afterwards.
I'll speak to the launch window question. When we began this project, we wanted to have a backup launch window in mind. So we designed the spacecraft to be light enough that we can fly without the Jupiter gravity assist. We can go direct descent to Pluto. And our backup launch window is next February, in February of 2007. It's about a 2-week launch window. The penalty for that is that it's a longer flight time without that boost in speed that Glenn spoke to. When we arrive, we won't have Jupiter en route to help us arrive earlier. So the arrival time would be 2019 or 2020. But keep in mind, the success of this mission is getting the goods at Pluto, Charon, and the Kuiper Belt. So as Andy said, our objective is to get off to a good launch and make sure that the spacecraft, the entire system, is ready to go. We'll fly it when we're ready, and then we'll make some history.
Okay, we're going to go to Aviation Week, I believe.
Yeah, hi, can you hear me okay?
Read you loud and clear.
Hello there, Dwayne, can you hear me okay?
Loud and clear, go ahead.
A couple questions on the Jupiter flyby. Can you describe in some detail the engineering rehearsals you'll do on the Jupiter flyby and some of the specific science you'll be able to get when you go through the Jovian system, obviously given Galileo spent so long there?
Well, the first part of it is we'll basically start mimicking the maneuvers that we will do at Pluto. We'll be pointing the cameras at the moons of Pluto, of Jupiter rather, and so we'll be able to check out all the commanding and the pointing of cameras as you're traveling by them. So that's the kind of engineering checkout. And then from that, we'll gather data that will be interesting to the scientists, and Alan can probably take that part best.
Yeah, Craig, we will be the 8th mission to Jupiter. But one of the dirty little secrets of New Horizons is that we'll be returning more bits from Jupiter than from Pluto because we have such greater bandwidth. We can dump our mass memory a number of times, which we don't have the capability to do in real time as we're flying by Pluto. We have a wide variety of experiments planned to test out our instruments, but also to fill in the gaps and to answer some of the questions that the Galileo mission left us with. A couple of particular areas I want to mention is that we'll be doing a lot of study of the dynamics of Jupiter's atmosphere. This is something that Galileo unfortunately wasn't able to accomplish because of its antenna problems, not having the bandwidth to send home essentially motion picture sequences of the dynamics of storm systems in Jupiter's atmosphere. Additionally, our route of flight from Jupiter to Pluto takes us directly down Jupiter's magnetotail out to 1,000 Jovian radii. And this is just a spectacular opportunity for magnetospheric science. Nothing like this has ever been flown, not only at a giant planet, at any planet. Even at the Earth, there has never been an equivalent flyby, a fly-through of a magnetotail like this. We have 2 very fine plasma instruments and a dust instrument, all of which will be on throughout that period in the weeks and months following the Jupiter encounter. We also plan studies of Jupiter's aurora, the satellite system, and Jupiter's faint ring. So it's going to be a busy time.
Okay, New York Times, go ahead.
Warren Leary, New York Times. A couple of things on that last answer, in fact. Any concern about going through Jupiter and having radiation damage from its belt? And then I have other questions.
No, we're about 30 RJ, or 30 times the radius of Jupiter itself, away from the planet when we do this flyby. The total radiation requirement for the mission is relatively modest to begin with, and the Jupiter flyby contributes just a portion of that. So it's really not a driver in the mission design or in the design of the spacecraft itself.
My next question is about the encounter with Pluto. Are there any concerns about how close you get to Pluto and Charon and possibly hitting a debris field of some type in the plane of the moons? How are you going to target once you get there, and how far away are you going to get from each body? And what are the concerns about possible debris?
You're asking excellent questions, and in fact questions that we wouldn't have asked for ourselves if we didn't have the discoveries of the new moons just very recently. Because of the propulsion system on board, which is very capable, we have the opportunity to change our route of flight through the Pluto-Charon system, even very late in the encounter, where we to discover something unexpected. Our plan, however, is to fly about halfway between Pluto and Charon, splitting that difference between them. But it's contingent upon some work that we need to do with the Hubble Space Telescope to ensure that we avoid any potential debris fields. Those would nominally be associated with the orbits of the small satellites, which might, as you may know, generate rings in the system. We want to make sure that we would not fly through those rings or ringlets. So we want to do deeper searches for additional satellites, and we want to pin down their orbits so that as we fly through that bullseye, we fly between satellite orbits with good separation and not at the distances that ring system debris may be present.
Okay, we're going to move to the Denver Post.
A last question, if I'm permitted. At this stage, how much of Pluto and Charon do you think you will be imaging and scanning? A full 100% of each body or 80%? What is your goal?
The goal is to map all of the sunlit portions of Pluto, Charon, and all of its satellites. I say sunlit portions because Pluto is tilted on its side and moving from an equinox to a solstice to a winter-type position, so that one hemisphere, the polar regions of one hemisphere, is increasingly in darkness, and we won't be able to image in that polar night. But other than that, we expect to map all the sunlit terrains. In fact, one of the reasons that we carry the LORRI instrument with its long focal length telescope is to allow us to see the so-called far sides of Pluto and Charon from quite a distance off during the approach. And of course, we will fly right off the deck over the close approach hemispheres of both Pluto and Charon on the actual day of closest approach.
Okay, now I believe we're ready to go to the Denver Post.
Yeah, this is Katie Human from the Denver Post. I have more detail on a question that's already been asked. Can you guys tell us exactly what you think is wrong with the booster rocket? What was found in that test run in September? Why do you suspect there could be a problem with the one bearing Pluto? And what are you guys doing to make sure that problem doesn't exist?
Let me just say that we really don't have all the details at this point. We hope to have more details at the end of this week or sometime this week, and I will give you a call and we can see if we can give you what we know at this point, but we really don't have those details. So if we can just stay on the science, and we will try to get those answers for you when they're available. Thank you. Do you have another question, Denver Post?
Oh, thanks.
Kennedy.
Yes, Dan Billow from WESH-TV. Two parts here. Do you consider the problem with the propellant tank resolved, yes or no? And what is the penalty, if any, for flying later in this window? In other words, if you fly later, more towards February 14th, is there an arrival time penalty for you later in the window?
The processing and inspection they're doing, but I think they can talk about the window.
Yeah, as we move through the window, after, well, the first portion of the window, we can make this very rapid transit where we arrive in the summer of 2015, 9-year transit across the solar system. And then we have a few days in the launch window, and there's a graphic in the press kit that shows this. A few days when we can arrive in 2016, and then a few days we arrive in 2017, and so forth and so on, until the launch window closes with an arrival date of the year 2020.
Any other questions, Dan?
Mike Schneider, Associated Press. If New Horizons is the first launch of an unexplored planet since 1977, why has it taken so long to finally explore Pluto?
Well, we've had a number of missions in space. The Voyagers, the Pioneers, we've got the 70s and 80s, 90s. And so while we've had those assets up in space making discoveries, we've been planning on future missions, and Pluto is just next in the queue.
I think I'll chip in with Andy on that, and just say that you know, at the time of the Voyager missions in the early 70s, really the importance of Pluto and of course the Kuiper Belt, because it wasn't discovered, wasn't appreciated at all. So it wasn't very high on the priority list because we didn't realize how much it had to teach us about the origin of the solar system and some of the kinds of physics, particularly atmospheric physics, that we want to learn about. Today, with our better knowledge of the geography of our solar system, we see how central it is to modern planetary science. And so I think it wasn't ripe for a mission from a scientific standpoint. And of course, if you're not at the top of the scientific queue, then you won't be at the top of the budget queue, because there will always be missions that are higher in priority. So Pluto's time came to fruition in the late 1990s and at the turn to this decade. And as a result, we built New Horizons to fly it there to return data in the next decade.
Okay, we're going to go to the daily camera. Are you on the line?
I am, yeah. The question I have is this is Todd Neff from the Daily Camera, where the current testing of the spacecraft is, what's being done right now, when it is scheduled to go into the Alice 5 fairing.
Well, that event actually occurred on Saturday, the day before yesterday. We are now mated to the launch vehicle in the Launch Complex 41 at KSC. We have not yet attached the flight nuclear power source to the spacecraft yet. That event is upcoming, after which we'll run some checkouts and some electrical tests to ensure that the mating operation went okay and everything is ready for launch. So we're in the final phases of the test campaign preparing for launch.
Okay, I believe we're going back to Aviation Week. Craig?
Okay, thanks a lot. Can you hear me okay?
Read you loud and clear. Go ahead, Craig.
Okay, a kind of a ceremonial question here. I understand you're really not carrying any plaques or records like Voyager, but what might be tucked inside that is of a commemorative nature?
Well, one thing you may have heard about is that we offered an opportunity for interested citizens, anyone in the public, through the internet, to fly their name to Pluto, and there's a CD-ROM on board the spacecraft with all of those names. We can get you the number of names. It's about 500,000, as I recall.
Any more commemorative beyond the ride sharing?
Well, the spacecraft carries the flag of the United States, and we'll talk to you after launch.
Any other further questions? Okay, any questions here? Yes.
Yeah, Robert Boyd again. The great debate of the day. How do you fellows come down on the Pluto planet or KBL? You guys.
Well, they have to vote because they know what I would say.
Yes.
Vote the way I told them. No, I think it's a settled matter. I think for the most part that we've really gone through a revolution, a paradigm shift in planetary science. We really just didn't realize the diversity of planetary types in our solar system. Pluto looked like a misfit because it was the only one we saw, and just as a Chihuahua is still a dog, these ice dwarfs are still planetary bodies. They're large enough to make themselves round by self-gravity, and they surely pass the test of planethood. So it's really quite an opportunity to first find that your notions were wrong. It's almost like a Copernican revolution. That the misfit becomes the average. The Pluto-like objects are more typical in our solar system than the nearby planets we first knew. And the opportunity is to go now and have a chance to study this most common type of planetary body in the solar system for the first time.
Any final questions here? Okay, I think that's going to do it for us. I want to thank you for joining us.
The reason we're interested in Pluto is because it's a window into the ancient solar system. It's a chance to look back in the history of the formation of the planets and to see worlds formed over 4 billion years ago and kept in the deep freeze, preserved as they once were ever since. It's very important that we go now. Pluto's moving away from the sun, and that not only makes the journey longer and the communications harder when we get there, but additionally it hurts our science, because as Pluto moves away from the sun, it cools, and its atmosphere literally snows. We call it collapses onto the surface. In fact, in 20 years' time, we expect that there'll be no atmosphere to study, so we're racing against that clock to make sure that we can study Pluto's temporary atmosphere. Well, Charon and Pluto are very different objects, even though they were formed in the same region of the solar system. Their surface brightnesses, their colors, their surface compositions are very different. Charon has an older surface than Pluto's because it has no atmosphere, no erosion processes. So by studying Charon, we not only get a glimpse at a different kind of Kuiper Belt object, but we also get to see recorded on its surface the history of impacts in the outer solar system for 4 billion years.
What are the Kuiper Belt objects, and where do they play in?
Well, the Kuiper Belt objects are those bodies, asteroid-like bodies, formed in the deep outer solar system that orbit in the same region, this disk-like region called the Kuiper Belt, same region as Pluto. And their role in this mission is twofold. One, Pluto's the king of the Kuiper Belt, so we're going to the largest object we know of in the Kuiper Belt to study that object and its retinue of satellites. Additionally, we hope to go on after Pluto if the spacecraft is in good health and fly by at least one, and maybe as many as two, ancient, smaller Kuiper Belt objects. You know, as we're flying up to the Pluto system, we'll see these little points of light become spheres, and first little marbles in the distance, and then grow to just be the enormous things that they are, entire worlds that we're studying with this sophisticated complement of instruments. I think the discoveries of the new moons really make it a lot more exciting. You know, in our wildest dreams, we hoped to go by 4 objects in the Kuiper Belt, and now we're going to get 4 just on the Pluto flyby. Maybe even more, because there are more moons. It's really made the Pluto system all the much richer. It's the history of planetary exploration that nature always rewards us by getting a close-up view. And we have never been to this exotica of the Kuiper Belt before. I think we're going to learn a great deal about how the solar system formed, about the bombardment history of the solar system, about how double planets work, about how rapidly escaping atmospheres work. There's so many presents inside the bag that I don't know where we're going to begin. Academy, in fact, ranked the mission so high because it was a Kuiper Belt mission, because the Kuiper Belt is the frontier of our solar system. It's the frontier of our knowledge. And it's a fossil record of the formation of the early days. So by traveling to the Kuiper Belt, we'll have a chance to unravel that history like a archaeological dig back into the history of our solar system.
I gotta go find one. I know. Well, everything here, I do find this stuff. Right.
following profile details the important events of the mission using approximate times. The Atlas RD-180 engine and 5 solid rocket boosters, SRBs, fire to lift the vehicle away from the pad. At 85 feet into its flight, Atlas begins its initial pitch, yaw, and roll maneuvers to attain the proper ascent profile. This will minimize aerodynamic loads. At 5 seconds into flight, the RD-180 engine is throttled down in preparation for the rocket experiencing maximum dynamic pressure. Approximately 27 seconds into flight, the combined pitch and roll program is complete, and the vehicle begins a near-zero angle of attack phase that will last until after the SRBs are jettisoned. After passing through the maximum dynamic pressure region at approximately 45 seconds into flight, the RD-180 engine is throttled up to 86%. The SRBs burn out after approximately 1 minute 33 seconds into flight. At this point, the RD-180 engine is throttled up to 100%. 13 seconds after burnout, the first 2 SRBs are jettisoned, followed by the 3rd, 4th, and 5th SRB 1.5 seconds later. 7 seconds after the second jettison, the closed-loop guidance steering is initiated. At this point, the RD-180 engine begins a ramped throttle where the engine maintains constant acceleration at 2.5 Gs. The payload ferrying PLF is jettisoned at 3 minutes 23 seconds into the mission. 5 seconds after PLF jettison, the forward load reactor, the FLR, is jettisoned. The FLR is designed to minimize motion between the PLF and the spacecraft during launch. 10 seconds before booster engine cutoff, the RD-180 is throttled down to maintain 4.6 Gs. Burning propellant at a rate of more than 1,600 pounds per second, the Atlas is more than 93 miles in altitude, 331 miles downrange, and traveling at a speed of more than 13,324 miles per hour. Booster engine cutoff occurs 4 minutes and 27 seconds into flight. After 6 seconds, the booster section is jettisoned from the Centaur upper stage. Main engine start, or MES-1, takes place at 4 minutes 43 seconds into the flight. Centaur and its payload are now in first burn. This 5-minute 23-second burn will inject the vehicle into a slightly elliptical parking orbit. After first burn main engine cutoff, MECO-1, Centaur, with its spacecraft, enters a coast period of between 8 and 24 minutes. While the time of flight for the following events depends on the actual launch day inside of the launch window, the Centaur's main engines are next reignited to burn for about 10 minutes. After Centaur's second burn main engine cutoff, MECO-2, the Centaur and the Star 48B third stage prepare to separate 13 seconds later. The Star 48B engine will burn for approximately 1 minute and 28 seconds. Spacecraft separation is to occur approximately 3 minutes and 27 seconds after engine burnout of the Star 48B engine and from 34 to 50 minutes after liftoff, depending on the actual launch date. As the New Horizons spacecraft departs the Earth gravitational pull, it will be moving at a relative speed of 35,000 miles per hour, or Mach 50.
Good afternoon, everyone, and welcome to our New Horizons mission science briefing. Here to talk about the New Horizons mission to Pluto and the Kuiper Belt is Dr. Melissa McGrath, the Deputy Director for the Solar System Division at NASA headquarters in Washington. Dr. Alan Stern, the New Horizons Principal Investigator from the Southwest Research Institute in Boulder, Colorado. Dr. Richard Benzel, the Science Team Co-Investigator from the Massachusetts Institute of Technology in Cambridge, Massachusetts. Dr. William McKinnon, the Science Team Co-Investigator from Washington University in St. Louis, Missouri. Dr. Dale Cruikshank, the Science Team Co-Investigator from the NASA Ames Research Center at Moffett Field, California. And Fran Bagenal, the Science Team Co-Investigator from the University of Colorado in Boulder. And we'll begin first with Dr. Melissa McGrath from NASA headquarters.
Good afternoon. It's a pleasure to be here this afternoon on behalf of NASA to introduce the mission science briefing followed by the spacecraft briefing for the launch of NASA's New Horizons mission to Pluto. New Horizons is the first in NASA's newest solar system exploration mission line called New Frontiers, which is a medium-cost mission line designed to provide versatility and flexibility and breadth to NASA's existing low-cost and more frequent Discovery mission line. We've thoughtfully planned a double whammy for you this week with two record-setting events. This morning, NASA's Stardust Discovery mission landed its sample return capsule safely in Utah. That capsule was the fastest man-made object to ever enter the Earth's atmosphere at 29,000 miles per hour. Likewise, on the outbound journey, the New Horizons spacecraft, our small little spacecraft sitting atop the huge Atlas rocket, will be hurtled toward Pluto. As you've heard several times already, it will be the fastest spacecraft ever launched from Earth. New Horizons will be the first mission to Pluto, the outermost and smallest planet in our solar system. Alan and his team will provide more details on the science objectives for the mission. Let me just end by saying, reminding you all that whenever we go someplace new, which will be our mission to Pluto, we always find something totally unexpected in addition to the planned science objectives. And we totally expect that to be the case for this mission to Pluto. So good travels to New Horizons. Good luck to its team. NASA is very proud to lead the exploration of new frontiers with this mission. Thank you.
Thank you, Dr. McGrath. And now to Alan Stern, the principal investigator for New Horizons from the Southwest Research Institute in Boulder, Colorado. Dr. Stern?
Thank you, George. Welcome everybody this afternoon. I like to call this mission the Everest of planetary exploration, and I just think it's fantastic. We are, after a very long journey, 2 days, right about now, from the middle of the launch window on Tuesday, and we're really looking forward to that. I'm going to tell you, as will this team here on the dais, about why this mission has so many gems in it that it rose to the top of the Planetary Decadal Survey as #1 on the runway for a new start in this decade. That's why it became New Frontiers 1. But before I do that, I want to make just a couple of special introductory remarks. First, I want to introduce Mr. Bruce Betts of the Planetary Society. Bruce, if you just raise your hand. He's available later for questions. I want to point out that this mission is a big team effort. Lots of organizations, people around the country. Some of them are represented in the various daises, the panels that are coming up here, and there are others like the Planetary Society that have played an important role, and many of them are converging, of course, on the launch site for this fantastic event that we're about to witness in a couple days. Secondly, I want to introduce some very special guests. As you know, Pluto is the only planet discovered by an American, discovered by Clyde Tombaugh. Clyde would be 100 years old next month. Unfortunately, Clyde passed away in 1997. But his wife, Patsy, is here today. Patsy, if you could stand up. Clyde's two children are also coming to the launch. Annette, would you stand up? Clyde's son, Alden, has not yet arrived. I guess his flight's coming in a little bit later in the day, but his son-in-law, Annette's husband, Wilbur, is also here, Wilbur Seitz. And we are very glad that you could come and be a part of this, and they'll be available for questions afterwards as well. So now I'm going to turn to the science, and my portion of the science is to set a little bit of the background, a little bit of the larger scope for why we're doing this mission. I'm going to talk to you about the Kuiper Belt and Pluto's context for just a couple of minutes. If I can have the first chart, the first slide. In this slide you see the architecture of the solar system on a gargantuan scale. It's such a grand scale that the orbits of the inner planets aren't even visible. The white circles are the orbits of the four outer planets, Jupiter, Saturn, Uranus, and Neptune, lying in the same plane, of course, as the inner planets. And beyond that, the orange or yellowish orbit is Pluto's orbit, discovered in 1930 by Clyde Tombaugh. Of course, Pluto looked like a misfit at the time of its discovery. It didn't fit the pattern of the four rocky terrestrial planets, followed by the four gas giants. It really was a different kind of beast altogether. But with the march of technology, we were able to see its context. And that took until the 1990s, fully 60 years after Pluto was discovered, to realize that Pluto is just the brightest of a very large ensemble of objects that orbit in the Kuiper Belt, a fossil relic of the formation of our solar system. This is the largest structure in our solar system. It is the home of most of the planets, albeit most of the miniature planets that we like to call ice dwarfs. And of course, it's the home of Pluto, our primary target on this mission. If I can have the next slide, let me show you that Pluto is not alone. Not only is it orbiting with this vast assemblage of comets and larger sized objects, but in that assemblage, the very tip of the iceberg, are large numbers of miniature planets. Technically, in fact, they're planetary embryos. These are objects that were growing to planethood, reached the mid-stage of accretion, a technical term, where they are accelerating in their growth due to what's called gravitational focusing, in a runaway process where they very quickly sweep up all the material and in very short order go from objects the size of counties to the size of countries and then worlds. But something, and we don't understand what yet, cut off the accretion process, stopped that process of growth in mid-gestation, and left us with this fantastic relic, this forensic evidence of planets that were arrested in the mid-stage of growth. And you see in that second slide, if I can have it back, the sizes of these worlds in comparison to the Earth and the Moon. They're tiny. This is why we call them dwarfs, ice dwarfs, because their surfaces are covered in ices. And it's really been a revolution in my field, in our field, to see that the solar system is so vastly populated that the outer solar system, in fact, was very good at making planets, particularly tiny ones, in the early days. So I'll have to take the third and last slide now and just sort of paint for you a picture of our view just a little over a decade ago and contrast it to our view today. Of course, we all grew up and went to school and learned in grade school that there were 9 planets. But today, by a fair count, we use the criteria of gravitational dominance, the one that many people like. It causes planets, in fact, to be spherical. We know of about 17 objects that qualify as planets, most of them, in fact, ice dwarfs. So, in fact, our view has really radically shifted from what we expected to be just the 9 planets, as Melissa pointed out, to what we think, after we finish the surveys, could result in hundreds of planets found in the outer solar system, most of them not terrestrial planets, not gas giants, but in fact ice dwarfs. So as I've said before, the misfit becomes the average. Pluto is typical of what is probably the most populous class of planet in our solar system. As you will hear, it has an atmosphere, a fascinating surface, a diverse set of moons, and in all of those respects, it probably mimics other Kuiper Belt objects, these other objects that I was talking about, which we won't be able to visit on this mission, the larger ones, but we will sample their building blocks, the smaller Kuiper Belt objects, out of which objects like Pluto were built. So we've really seen a revolution in the field, and this contributed very much to the impetus to fly this mission. And I think with that, I'll turn it back to George.
All right, thank you, Alan. We'll turn now to Dr. Richard Benzel, the science team co-investigator from MIT, the Massachusetts Institute of Technology in Cambridge. Dr. Benzel?
Thank you, George. I'm going to speak to what we know about Pluto, or our basic knowledge about Pluto. And in fact, in some ways, our basic knowledge about Pluto could all fit on a 3x5 card. But the New Horizons mission isn't about filling up 3x5 cards of new information. It's about basic exploration. This mission is going to the far frontier of our solar system, a place where nature operates in environments and temperatures vastly different than anything we experience normally here on Earth. So we want to go explore to see what's out there, to try to understand what new things can we learn. And if I could have the first slide. This is an example of the best kind of image that we can get of Pluto with the Hubble Space Telescope. That's the image on the left. And there's a familiar object in the middle that if this was all we could see, imagine how difficult it would be to understand. And that picture in the middle is the Earth's moon at the same resolution. Now, of course, you know that we see the moon with much greater resolution, both in terms of spatial resolution, but also understanding its composition. So we have a much better idea, understanding of all the amazing things there, an amazing history of the moon that we know simply because it's close by and we've been able to explore it by spacecraft. So I want to talk now about how we've been able to learn some of the things we have learned about Pluto, and it's taken some pretty amazing or clever tricks with nature. And if I could have the next slide, please. Back in the mid-1980s, the orbit of Pluto's moon Charon could be viewed edge-on from the Earth. And during this edge-on viewing of the orbit of the moon, it would eclipse in front and behind the planet. And each time the moon would go in front of the planet, for example, it was like a scan across the disk of Pluto. Even though our largest telescopes couldn't make out anything on the disk, we could carefully watch, monitor the brightness of the Pluto-Charon system to try to understand what it was that the moon was covering up. And through a long series of eclipses over about 5 years, we were able to put together a map of what we think Pluto's surface looks like. And if we could have the next slide, please. So this is a map, reconstructed map from these mutual eclipses between Pluto and its moon of the surface of Pluto, and we see that it's very differentiated or variegated on its surface. We see bright regions, particularly at the bottom. We think that's a large polar cap on Pluto, and this all plays into our understanding of what we think Pluto is made of. We think basically Pluto is made of nitrogen ice, methane ice, carbon monoxide ice, frozen water, maybe rock mixed in. And the fact that we see different markings on the surface tell us that there must be some interplay or even some seasonal variations on Pluto. And something that would drive the seasons is the presence of an atmosphere. And we had to be clever in even knowing there was an atmosphere around Pluto. If we could see the next slide, please. One of the ways we were trying to be clever in discovering or understanding the atmosphere of Pluto is through a kind of event called an occultation. And this illustrates on the right a star that happens to be passing behind Pluto. And as it gets very close to the edge of the planet, the light from the star dims very gradually and then disappears behind the planet. And it's that gradual dimming as the star went behind and then came out the other side behind Pluto that told us that Pluto has an atmosphere and began to tell us something about how much atmosphere it has. And we think that atmosphere has the basic elements that we see on the surface, things like nitrogen, methane, carbon monoxide, and that as Pluto comes closest to the sun, it gets warm enough for the ices on the surface to turn into gas to go into the atmosphere. And as Pluto is now going away from the sun and is part of its 248-year orbit, there may come a point when all of those gases in the atmosphere freeze out and land back on the surface. George?
Thank you, Richard. Our next science team co-investigator is Dr. William McKinnon from the Washington University at St. Louis, Missouri. Dr. McKinnon?
Thank you, George. You know, another important reason to study Pluto and its moon Charon is because together they form a binary planet. If I could have the first slide. Here you see a picture of, we often refer to the Earth and the Moon as binary planets, and this picture illustrates the Earth and Moon to scale, and the Moon looks pretty large, but in actuality it's only about 1% of the mass of the Earth. Now, Charon, Pluto's moon, is in comparison almost a full 10% of the mass of Pluto. So in terms of binarity, if you like, I mean, Pluto is the real deal. So we want to know how binary planets like our own form. And, the leading theory right now for the Earth and the Moon is that it formed through a massive, giant collision early in solar system history. And we also think the same thing applies to Pluto and its moon. Can we look at the next slide, please? Now, this is a detailed, sophisticated computer simulation how Pluto and its moon might have formed. And this was recently published by Robin Canup of the Southwest Research Institute. And what you see in the upper left panel is the moment of collision between two ancient bodies in the Kuiper Belt. They've approached each other, drawn by their mutual gravity, and the collision is actually relatively slow by solar system standards, maybe about 1 mile per second. Still faster than a speeding bullet, so it's okay. The collision disrupts the bodies. You see the progress of the collision moving from the upper left to the upper right. You see it's moving, the body has moved, the colliding bodies come in from the right, and it's collided, and now it's moving in a counterclockwise way around the sort of maybe early version of Pluto. You see it's stretched out enormously. It almost looks like a giant mango or banana, something like that. But eventually it draws itself up. Down in the lower left, you see it's becoming more spherical, and after several orbits and maybe about a day of time, an Earth day of time, we see something that looks very much like Pluto and its present moon. One of the differences in this computer simulation, you can see a color coding in the lower right corner after things are over. Part of what we can now call Pluto is yellow and red, and those mean greatly increased temperatures, enough to melt the ices that Rick Binzel was just talking about, and probably forming an early ocean on the planet Pluto. So when we get to Pluto in about 9.5 years, we will be taking a very close look at Pluto and its moon to see what differences and similarities there are. We'll be comparing those to the differences and similarities between our Earth and moon and to our theoretical models. And it turns out that going to the Kuiper Belt is one of the best things we can do to study binary planets, because astronomical images right now, such as taken from the ground in Hubble Space Telescope, have shown us that maybe 25% or maybe even more of all Kuiper Belt bodies and mini-planets are binary worlds. And that's not all. If I could have the next slide, please. Recently, in Hubble Space Telescope images, and by a team led by Hal Weaver of our mission, Pluto has been discovered to have 2 more moons. So it's not just the Pluto-Charon binary, it's actually the Pluto system. And what this picture shows is the orbits in projection, as seen from the Earth today, of Pluto, its moon, and smaller moons that we right now are only calling P1 and P2. We think that in a giant collision such as might have formed Charon, that there's so much debris blasted out that the formation of such smaller moon or moonlets is probably inevitable. And this, in fact, may be part of the evidence for that. And you can be sure that when we get to this system, we'll be using all our instruments to learn as much as we can about these 2 new moons and any other moons that still may be too small to be seen yet, but we may discover soon. Thank you. Thank you, George.
Thank you, Dr. McKinnon. And we'll learn now from our science team co-investigator, Dr. Dale Cruikshank from the NASA Ames Research Center in Moffett Field, California. Dale?
Thank you. This is a very exciting time. We are poised to begin the exploration of a new world, a world that we didn't even know existed until 1930 when Clyde Tombaugh discovered it. And for about 45 years after the discovery, we knew only 2 things about Pluto: where it was and its name. But about 30 years ago, we began to get the first inklings of what this little world is all about, when we used some of the large telescopes here on Earth to begin to make a new kind of measurement that had only been enabled by technology available in about 1975. And we learned, starting then and over the subsequent several years, that Pluto's surface is primarily covered with frozen gases, materials that we normally think of as gases: nitrogen, which fills this room, carbon monoxide, and methane, which is natural gas. But at the very, very low temperature of Pluto's surface, which is about 380 degrees below 0 Fahrenheit, those things are all solid, and they're frozen out as ices and frosts in a very complicated pattern on Pluto's surface. Let's have a look at the animation, please, which shows us at least a guess as to what Pluto might look like. And I want you to pay special attention to the color that you see in this animation here. It has a kind of pinkish orange color. And the gases that I mentioned, the ices that I mentioned, are not colored at all. In fact, they're very white, as we see with ordinary frozen water, snow and frost. So something is causing that pink color, that orange color of Pluto, and we think it's probably the presence of small amounts of complex organic material that has come from somewhere, we don't know for sure where, but has somehow deposited itself on the surface of Pluto and gives it that pinkish color. So that's one of the things we want to explore. We want to see also how these ices of different kinds, and we may discover new ones as well with the power that is given to us by the New Horizons spacecraft and the instruments that it carries. We want to see how those ices are distributed around Pluto's surface, and I should say also the ices on Charon's surface as well, the big moon. Those two objects must have their own geological structures. Everything we've looked at in the outer solar system has its own unique kind of geology, and so we're expecting the unexpected. We think we may see some of the kinds of things seen earlier as we've explored other bodies in the outer solar system, but we're prepared to be quite surprised as well. If I could see the slides for the first slide, please. This is a picture of Neptune's largest satellite, Triton, which in many ways is very similar to Pluto, comparable in size, comparable in temperature. We also see the frozen nitrogen and a few other gases frozen out on its surface. And what we discovered to our astonishment when we flew by Triton for our one and only close-up look in 1989 with the Voyager 2 spacecraft is that this frozen little world has an active geological history, an active geological present. It's doing things, and we may discover that Pluto is doing things as well. There may be geysers, there may be jets, there may be recent evidence of cracking and flow on the surface. We're prepared to be surprised. Let's look at the next slide, please. This is yet another icy object. This is one of the Cassini images of Saturn's moon Enceladus, which has a very young surface, geologically speaking, and shows evidence of geological activity that may be going on even at this moment. And then the next slide, please. We see another of Saturn's icy satellites. This one is called Iapetus, and it's covered, at least in part, by a dark reddish-orange material that we also have identified as organic in composition. And it may be a smattering of this kind of stuff that is also giving us the tint that Pluto shows as well. And then the last image is a portion of the very interesting surface of Jupiter's satellite Europa, a satellite that has a very young, again, geologically speaking, surface that's been cracked and tortured and bent and twisted in ways that may be characteristic of the icy moons and the icy bodies that we're about to explore with the New Horizons spacecraft. So we have a backlog or a body of information and ideas as to what we'll find in the outer solar system as we progress into Pluto and beyond. But we, as I said before, are certainly prepared to be surprised.
Thank you, Dr. Cruikshank. And to conclude our panel of Science Team co-investigators, we'll learn now from Dr. Fran Baganoff from the University of Colorado in Boulder. Fran?
Thank you. So Dale and Rick have told you that the frost on the surface of Pluto is evaporating and forming an atmosphere. Now, Pluto is a small planet and has a fairly weak gravity, and so this atmosphere is escaping and flowing away from Pluto. So you can think of Pluto as a giant, a colossal comet. In some ways, it acts very much like a comet. So I'm going to show you a series of slides as to how this works. So we can have the first slide, please. You'll see that Pluto's atmosphere is extensive, and as it escapes, it moves and flows away from the planet and goes extensive distances well beyond the orbit of Charon. And so then in the next slide, this atmosphere, which becomes ionized by the UV sunlight that ionizes the atmosphere, but it's embedded in the solar wind. Now, the solar wind is the atmosphere of the sun, the hot atmosphere that heats up and escapes from the sun and flows out through space and flows throughout the whole of the solar system out beyond all of the planets and flows past this atmosphere of Pluto that's escaping. So the interaction of this solar wind with the atmosphere is quite complicated. And the next slide shows you a computer simulation that we've made at the University of Colorado by Peter Delmare of the perturbation of the solar wind made by this very extensive atmosphere, ionized outer atmosphere of Pluto. And what happens is that the ionized material from Pluto is carried by the solar wind and pulled back into a big tail like a comet. And the last slide shows you that the ionized escaping material from Pluto forms large gyrating trajectories away. The ions move away from Pluto and are carried away. Now, the New Horizons spacecraft will carry instruments that will measure this interaction region, this complex interaction. And so the SWAP and PEPSI instruments, about which you will hear a little later, makes these measurements of this escaping atmosphere and will in fact measure the amount, the net amount, by looking at the perturbations in the solar wind and measuring those ions that are carried away. We will be able to measure the total amount that's escaping. And the amount is in fact adds up to be something significant, because over a period of 1 year, 3 million, I'm not Carl Sagan, 3 million tons of material comes from the surface of Pluto. Now, if you look at that in terms of the amount of surface ices that's removed, then over a period of 1 million years, you get a thickness of about 1 foot. So that doesn't sound like a whole lot. You've got a big planet there to remove. But if you then add that over the lifetime of Pluto, the 4.5 billion years of Pluto, you can see that you can actually remove substantial amounts of ice from the surface of Pluto over its age. So what we're finding is that we hope that when New Horizons flies through this region and makes these measurements by SWAP and PEPC and the measurements of the atmosphere, we'll actually be learning a lot about what's actually been happening on the surface, the net effect of which has a significant impact on the surface. So thank you very much.
All right, thank you, Fran. And we'll take questions now. Please, once again, give your name and affiliation when the microphone comes to you, and we'll start here in the front with Stefano.
Stefano Colodran, Time Magazine. What would have been the ideal launch date if you could have had everything you needed during this last, I don't know how many decades?
Why don't I try that one? That's a good question. In one respect, we have the ideal launch date because the payload that we're flying, as you'll hear in the next couple of sets of speakers, is a much more advanced payload than we could have flown, for example, in the last Jupiter launch window 10 years ago. Furthermore, we did not know of the Kuiper Belt in previous decades and would not have thought to design the spacecraft for that part of the mission or possibly been able to react to it. In terms of the optimal launch, one wants a Jupiter launch window because Jupiter boosts our speed equivalently to adding another stage to the rocket. A year down the road, out at 5 astronomical units, we'll get a 4 kilometer per second, a little over 2 mile per second boost from Jupiter. And that Jupiter window has extended for the past 3 years. We're at the very tail end of it. It closes on February 2nd, which is our impetus to fly by February 2nd, if possible. And we can go on. We've designed the spacecraft to be light enough to be lofted on direct descent to Pluto, but we would prefer that boost. The earlier dates, for example, in late 2004 and late 2003, that we could have also flown to Jupiter, would have been suitable to us, but they would have caused the spacecraft to have had to carry much more radiation shielding because it would have had to travel much closer, much deeper in Jupiter's radiation belts. And we would have again had to sacrifice payload to do that. So I think we have a very good launch window. That's the bottom line. Maybe the best we could have hoped for, despite the fact that nobody likes delayed gratification.
Craig?
Craig DeVault with Aviation Week. My apologies for a bit of an engineering question in a science briefing, but first things first here. On the first 2 or 3 months, well before Jupiter, can you kind of step through the really key engineering milestones on spacecraft as a whole or science instruments prep?
I think I'll do that one as well. Sure, absolutely. First couple of months, our objectives are first to put ourselves on the very precise trajectory that we need for the Pluto aim point at Jupiter. Nominally, the Atlas will deliver us there, but it'll make some tiny dispersion around the nominal trajectory, and we carry engines and a hydrazine propulsion system to make those tiny corrections. In fact, we may start as early as about +8 days into the flight to do that. We could perform as many as 3 maneuvers in the first couple of months to get that done. Then the spacecraft systems engineering team and the spacecraft mission operations team will be checking out all the flight subsystems, the flight software, the guidance systems, the onboard computers, the thermal system, etc., before we begin to then slowly, but over a period of several months, commission the entire payload, instrument by instrument. I want to point out that some of the instruments, because they're so sensitive to very low light levels, for example, can't be fully commissioned until we're pretty far from the sun. In fact, we have one part of one payload that can't be commissioned until we're almost at Uranus. But we will get most of the payload up and running by next summer in preparation for rehearsals for the Jupiter encounter. And that process will keep us pretty busy in those first months.
Additional questions? Bill.
Excuse me, Bill Harwood, CBS, with two quick questions. One, Alan, can you tell me, excuse me, the process you'll go through to identify a Kuiper Belt object beyond Pluto that you eventually, I don't understand how, you don't have it today, but you will then. What do you have to do? And the second one, maybe for Dale, that picture of Triton was one I was thinking about earlier. Would you expect pictures, lighting with your cameras and all of that? Will it be similar to those kinds of pictures from a brightness standpoint, detail, that kind of thing?
You want that answer first?
Yeah,
okay,
go ahead.
Let me just say, yeah, we'll certainly get to see that much of Pluto's surface and quite a lot more than we were able to examine at Triton. Even though we're flying by very fast, we have the long-range camera, which gives us a detailed view far out, and then when we get up closer in proximity, we'll be seeing the other face of Pluto, but basically able to map the entire thing at substantial high resolution. Now, the sun is a little bit fainter, as seen from Pluto's slightly increased distance, a few more, well, a few percent less than the lighting at Triton. And Pluto's surface is not quite as bright either. Triton's surface has a much fresher look to it in the sense of more freshly deposited ices and snows of various kinds. But it won't be that different. And so we expect to have at least as good a look at Pluto overall as we had a look at Triton.
Okay, I'll speak to finding Kuiper Belt objects. Well, I said a little bit earlier, people don't like delayed gratification. And there are a lot of people that don't, they're having trouble handling the fact that we're launching to some targets that we haven't picked yet. But actually, we're going to know so much more about the Kuiper Belt in 10 years that, from my chair, it's just premature. Let me tell you how we'll go about it, but first you have to understand just a little bit about the orbital mechanics. As you heard earlier, we're going to be screaming through the outer solar system at 14 kilometers per second. And we have some small engines on board that can change our trajectory very slightly around that. So after we pass Pluto, when we make an engine maneuver, we can then access a little cone of space behind Pluto that's only 1/10 of a degree in opening angle. It's a very narrow cone stretched out over billions of kilometers. Based on what we know of the Kuiper Belt, there should be about a half a dozen KBOs in that cone that we could access any one of, or possibly two of if we have enough fuel. So what we're going to be doing beginning in about the year 2012, beginning about 3 years before encounter, is making a search of the region where that cone will lie. But it's like skeet shooting. We have to lead where it will be when we get to Pluto so that we search in 2012, a little bit ahead. We will find approximately a half a dozen objects that will be candidates. We'll turn them over to people like Rick and Dale, who'll be making spectra, studying their colors, looking for moons, doing all the properties, so we can pick our favorite, which one will deliver the most bang per buck, or most bits for what we can do. And then we'll pick our #1 target and our #2 target and see if we have the propellant to do both. And then we'll reach them in sequence if we're approved for an extended mission.
All right, we're going to stop right here so that we can change panelists once again and learn something about the spacecraft that's going to bring us all this wonderful science. So we'll be back in just a couple of minutes with our panelists, two briefings, back to back on the New Horizons spacecraft. Thank you. Good afternoon once again, and this portion of our briefing is on the New Horizons spacecraft. This will be a two-part briefing, and our first four presenters for part one will begin with Dr. Hal Weaver, the New Horizons project scientist from Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland. He will be followed by Dennis Reuter, the Ralph instrument scientist from NASA's Goddard Space Flight Center in Greenbelt, Maryland. Once again, Dr. Alan Stern, the Alice instrument principal investigator from the Southwest Research Institute in Boulder, Colorado. And to conclude part one of the spacecraft briefing is Lynn Tyler, the REX, or Radio Science principal investigator from Stanford University in Palo Alto, California. Now we'll begin first with Dr. Hal Weaver. Hal?
Thanks, George. Hello, everyone. You just heard in the previous briefing about the many exciting scientific objectives of the New Horizons mission. Science is the driver of this mission. And this is the reason why NASA is embarking on this exciting journey to the outskirts of the solar system. But in this briefing, we're going to shift gears a little bit and talk about how we're going to accomplish those exciting scientific objectives. And to do that, we need a highly capable suite of scientific instruments, and that's exactly what New Horizons has. Now, back in the mid-1990s, NASA made an investment in a development program to produce lightweight, energy-efficient, and highly sensitive instruments that can be used to explore the outer solar system. And the New Horizons instruments, many of them anyway, are the fruit of that investment in that NASA program. Now, all 7 of the scientific instruments on New Horizons totaled up together weigh about 100 pounds, hardly anything. But even more amazing, you know, the power drawn by these instruments is about the power that you would draw from a night light in your home. The light levels at Pluto are about 1,000 times fainter than here on Earth. And you know, the particle densities are also much lower there. So these instruments not only have to be lightweight and energy efficient, but they also have to be highly sensitive. And they have to be able to count just about every photon of light and every particle at Pluto. Now, if you look at this graphic, this is the New Horizons spacecraft. And as you probably have heard, it's about the size of a piano and weighs about 1,000 pounds. And all the scientific instruments are located around the periphery of the spacecraft. And the primary purpose is to get the scientific goods at Pluto. And with that, let's talk about each one of these scientific instruments.
All right, thank you, Hal. And we'll go now to Dennis Reuter from the Ralph instrument from Goddard.
Good afternoon. I'd like to introduce you to Ralph, the visible infrared imager on New Horizons. Could I have the first slide, please? Ralph, as I said, is a visible infrared imager, but it's actually 2 instruments in one. It's MVIC, the multispectral visible infrared, imaging camera, and LISA, the linear etalon imaging spectral array. LISA is an infrared camera. Now, MVIC will give us an image of Pluto as we go by. It's like what you would see if you were on the spacecraft and you had big eyes. It gives us a black and white camera that lets us see shades of lighting. It tells us about the surface, tells us about the geography and the morphology of the surface. MVIC also has color cameras on it, 4 color cameras on it. There's a red camera, a blue camera, there's a near-infrared camera, a little bit longer than what we'd see, and a methane camera. Now, those color cameras are going to tell us about what the surface is made of. It's going to tell us the type of surface we have and the type of processes that are going on. LISA is a infrared camera, meaning that it doesn't looks in light that we can't see, but what it does is it's not only a camera, it breaks the camera into the light that's reflected from the surface, the solar light that's reflected from the surface, into about 250 wavelengths, 250 colors in the infrared. Not visible colors, but the same sort of thing. These colors are very sharp, and by looking at those colors, we can tell what's on the surface. We can differentiate methane from CO, from water vapor, or from water, by looking at the distribution of the light in the different colors. It will also let us find more complex species that have been mentioned before. The suspicion is that we have more complex hydrocarbons and other species on the surface. So LISA will not only allow us to see what's on the surface, it will allow us to map it out, where it is on the surface, and it will allow us to tell the physical properties of it. Is it a grain? Is it a frost? The combination of the two makes it a very capable instrument. It provides us our 2 primary goals, which are, again, geology, morphology, and composition, and allows us to do our secondary goal of temperature of the surface, because the colors that are emitted or reflected depend very sensitively on the temperature of the surface. So again, we can tease that out from just from looking at the colors of the surface in the infrared. Could I have the next slide, please? This is actually a picture of Ralph. Ralph is the instrument on the left, not the person working on it. And I won't go into the full details of the instrument, but I'd like to point out a few salient features. The white circles on the top are radiators. Because LISA has an infrared camera on it, it's sensitive to heat. If it's too hot, it's noisy. So we need something to cool it down. And the radiators cool LISA down, the camera down, to about 130 K. It's about minus 225 Fahrenheit. So it's operating very cold. The large black structure in the front of there, pointing towards the fellow, is the aperture. That's where the light comes in. And the two focal planes, the two actual cameras, the things that do the business, are on the side and the front of the instrument. It weighs about 20 pounds, and you can see it's pretty small, but it's a very capable instrument. Next slide, please. Now, Lisa was built, Ralph was built by a consortium, a very close-knit team that involved Ball Aerospace in Boulder, Colorado, NASA Goddard, Maryland, and Southwest Research Institute, the PI Home Institute, both in Boulder and also in San Antonio, Texas. It's the most capable instrument that's ever been sent on a reconnaissance mission. Talked about remember, it's got to operate in a light level that's 1,000 times dimmer than on the Earth, but it's delivering pictures that would be as if you went out and looked at bright sun out here. It's also, the way we get the spectra, we scan the planet, is we move the spacecraft, take pictures as we go along. And Ralph has in it a series of electronics that time the exposures so that we don't get any smearing while we're doing that. And it does all this for 7 watts of power, which is about half of a night light, if you will. We expect to get a lot of very interesting information out of Ralph. It should keep us and those who come after us busy for quite a while, establishing what's actually going on the surface.
George? Thank you, Dr. Reuter. And now for Ralph's other half, Alice. We'll hear anything from Dr. Alan Stern.
Yeah. A little bit of context. Ralph, Alice, and Rex form the core payload of the New Horizons mission. In the next 4 or 5 minutes, I'm going to tell you about Alice, Ralph's companion in space from here to eternity. Alice is our ultraviolet spectrometer, and whereas Ralph's job is to map the surface of Pluto, its satellites, and Kuiper Belt objects that we fly by, and determine the composition of the surface and the appearance of the surface, the objective of the Alice ultraviolet spectrometer, which works, of course, at shorter wavelengths, is to study the atmosphere of Pluto, its composition, and its structure. If I can have the first slide, you see Alice is located, in fact, and bore-sighted with the Ralph instrument. It's also bore-sighted with the Lori instrument that you'll hear a little bit about in the second portion of this presentation. Alice has got its primary job of doing the structural compositional measurement of Pluto's atmosphere. Its secondary job is to search for evidence of atmospheres around Kuiper Belt objects and Pluto's other moons. In fact, Alice is capable of detecting atmospheres that are as rarefied as 1/1000th of Pluto's atmosphere, which is already a pretty tenuous atmosphere. Alice uses 2 primary techniques. One is called air glow. It's really a passive technique where we point the telescope at the front end of Alice at our target, for example, Pluto. We see emissions glowing in the ultraviolet like the aurora, in a sense, and those tell us about the composition and temperature pressure structure of the atmosphere that we're observing. The second technique is called an occultation technique. It's an active technique. We will actually, as we fly behind Pluto or other objects, we will stare at the sun with this instrument and watch the sun set through the atmosphere to provide an active beam, a very powerful beam of ultraviolet light to probe the atmosphere as a function of altitude as the sun sets, and then on the other side of the world as it rises again. And I'll take the second chart. This is a picture of the Alice instrument. It's about a foot long. It's also a miniaturized instrument like many of the instruments of the New Horizons payload. It draws about 5 watts. That includes its flight microprocessor. It weighs about 4 kilograms. And it's one of a new generation of ultraviolet spectrometers that are not only very compact, but have removed the need for any moving parts to study the entire spectrum at once. I'll contrast it, for example, to the ultraviolet spectrometer on the previous Outer Planets reconnaissance mission, Voyager, which had 2 pixels in a much larger, much more power-hungry package. We have 32,000 pixels in a much smaller package. This instrument was also built by the Southwest Research Institute, and it is the most capable ultraviolet spectrometer ever flown on a reconnaissance mission to a planet. George.
All right. Thank you, Alan. And now to the radio science. Dr. Lynn Tyler, the Rex Principal Investigator.
Thank you. The Rex experiment, or radio experiment, is is different in two ways from the others that you hear about. By comparison with the other instruments, REX is highly focused on one objective, and that's the determination of the conditions on the surface of Pluto and just above the surface. So it's designed to measure the atmospheric structure in the region of perhaps some tens of kilometers above the surface, and to accurately determine the surface conditions. The second way in which it differs is that REX, a major portion of REX is on the Earth, and it works by the method of occultation, but in this case radio occultation. So the geometry is the same, the basic considerations are the same, but instead of having a telescope staring at a star, or in the case of Alice, the sun, we will use an artificial star, which is a NASA DSN transmitter on the ground. And our telescope will be the radio system on the New Horizons spacecraft. In the first graphic, the high gain antenna is highlighted there and labeled as REX. So that's our receiver, the antenna that collects the occultation signals, and there's some slight modifications to the internal electronics to acquire the data. So it's rather simple implementation on the spacecraft. But occultation requires special geometry, and that's been arranged to accommodate Alice and REX simultaneously by arriving at a time when, seen from Pluto, the Earth, and Sun all line up. So if we look at the Sun, we're also looking at Earth. If we're looking at Earth in the case of REX, we can see the signals from these uplink radio transmitters. So the geometry requires that the object to be studied pass between the source and the observer. In this case, we want Pluto's atmosphere to pass between the Earth or Earth-Sun and the spacecraft, and we do that by flying New Horizons behind Pluto, as seen from Earth, or Earth and Sun behind Pluto, as seen from the spacecraft. So in the animation, keeping in mind that the Earth and Sun are in the same directions, we should have an animation. There we go. You can see New Horizons approaching Pluto and turning to make these observations. And right about now, there's the solar-Earth occultation. That's the time that it occurs. And then there's some observations in the interval approaching Charon, but then the same thing happens again. Now here it's shown it's already occurred. We're passing behind Charon, but the geometry is arranged to provide these particular events. This is an operationally intense investigation because it requires cooperation between the ground and the spacecraft. So in the second graphic, you can see the two elements of REX, a 70 meter perhaps, or at least 34 meter antenna on the ground, radiating a very highly controlled signal at high power toward the REX receiver. And what we measure is not the dimming of the signal, but the time delay, the change in time delay as the signal passes above Pluto's atmospheres in comparison with when it passes through Pluto's atmosphere. And that'll be a few billionths of a second difference in time delay, but that's sufficient, if measured accurately, to determine well the temperature and pressure structure of Pluto's atmosphere. So this is also another first for New Horizons for the program, in that this is the first uplink experiment that is of this type that's been done.
George. Thank you, Dr. Tyler, and we'll take questions now for these four scientists. Please give your name and affiliation when the mic comes to you. Stefano.
Yeah, Stefano Clevent, the Time magazine. I've read probably maybe a week ago that there was a paper released that actually by scientists, was published, that Charon actually does not have an atmosphere. I don't know if you have read that and what do you think about it?
I'll say a word or two about that. There were a series of 3 teams that observed the stellar occultation in the visible of Charon last summer. This is a very rare event. There had been a previous occultation in 1980, which also indicated that Pluto's moon Charon had no atmosphere. Because of the march of technology and the fact that this was a brighter star, they were able to set even tighter constraints, that Charon's atmosphere can't be even a wisp of what Pluto has. And that was the outcome of this experiment published in Nature last week.
And it said that the atmosphere of Charon is at least a factor of 100 more tenuous than Pluto's, about a factor of 100 more, less atmosphere on Charon than on Pluto. That's the upper limit that was set on Charon's atmosphere.
Additional questions? Craig?
Craig Tavald, Aviation Week. I may be making a dangerous comparison here, so straighten me out. But from a qualitative point of view, would it be accurate to say as a reconnaissance, you're going to be doing as well on Pluto with the instruments that you got as Pioneer 10, 11, and Voyager 1 and 2 did, kind of combined on all of their flybys, their various planets?
In terms of the remote sensing investigations that we can do, and you can, let me step back a little bit. We are in most respects from the standpoint of remote sensing going to blow away what Voyager could have done had it ever gone to Pluto. More sensitive instrumentation, far more capability. To give you one example, what Dennis talked about in terms of a composition mapping spectrometer, Voyager didn't even carry. Its ultraviolet spectrometer was Stone Age by comparison to what we're flying. Its imager was much less sensitive and didn't have the kinds of long wavelength color capability that we have. Couldn't do thermal mapping either. We have a dust detector that Voyager didn't carry. Now, Voyager did carry instruments like magnetometers and wave instruments that are appropriate for the giant planets that we're not carrying. So there's a little bit of apples and oranges there, but from a pure standpoint of the appropriate investigations for Pluto and Kuiper Belt objects, this is probably an exaggeration, but only a little bit. We are light years ahead of what Voyager would have delivered.
We're going to stop and Bill, you got a quick one here? Okay.
Yeah, probably a dumb question too, but I know the transmission rates and your bandwidth at Pluto's distance are being what they are slow by, I guess, home computer standards. But can somebody give me a sense of what a typical image from the visible light cameras, which is what most public people will see, how big a file is that? Are they a megabyte? Are they a bunch of megabytes? What are they?
Yeah, the Eagle Eyes on New Horizons, which is the LORRI instrument, is a CCD camera, just like what you have in, a more sophisticated version of what we use in modern digital cameras, and that's a 1024 by 1024 pixel array, about 12 megabits of information, and we have to transmit those back at about 1,000 bits per second. So it takes a little while to get them back, although we compress those images also losslessly by about a factor of 1.5 or so. So we try to squeeze every little bit that we can and get the information back to the Earth as soon as possible.
All right, that's a good segue because we're going to hear about the LORRI instrument next. We're going to turn the dais very quickly and we'll be right back. Thank you. To conclude our briefing on the New Horizons spacecraft, we have 4 more instrumenters. We'll begin with Dr. Andrew Chang, the LORRI instrument principal investigator from Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland. He'll be followed by Dr. Ralph McNutt, the PEPSI instrument principal investigator from Johns Hopkins University. Dr. David McComas from the Southwest Research Institute will discuss the SWAP instrument as the principal investigator. And Tiffany Finley is the Student Desk Counter Project Manager from the University of Colorado at Boulder. And we'll begin first with Dr. Andrew Chang from Johns Hopkins.
Thank you. I'm the LORRI Principal Investigator, which means that I led a team of remarkably wonderful engineers led by Steve Conard, and also a company, SSG Precision Optronics, that actually built a telescope that I'll tell you about, that I'm going to brag about. Now, it's a little bit hard to talk about things that we're going to do when other people have been talking about things they've done, but I'll do my best. So the next slide we'll show you where LORRI is. It's a telescope that's inside the body of the spacecraft. Now, LORRI is our telephoto camera, and that means that's the instrument we use to zoom up as close as we can, get the most detail we can of the images. And so on the next slide, we see two drawings now of LORRI. On the left, it looks like a telescope, and you see the electronics box and the radiator plate hanging off the side and the blue tube looking at you. And on the right, there's a cutaway. And in this cutaway, you see LORRI looks like a more or less regular reflecting telescope. But actually, LORRI is very special. Let me tell you why LORRI is so special. We heard a little earlier from Dr. Cruikshank that we have, the last time we went out past the orbit of Neptune, we had a look at one of Pluto's very close cousins, the moon Triton, and we looked at remarkable images obtained by the Voyager spacecraft of Triton. Now let's just compare the camera that took that picture with LORRI. Now, the Voyager narrow-angle camera has more than twice the mass. It used more than twice the power. It had less than half the resolution. So the LORRI camera is getting more than twice the amount of detail that we would have seen. And in addition, it's several times more sensitive. So it has much greater low light capability, which you've also heard earlier we definitely need at Pluto. So there's even something else that's very special about LORRI, which is that because of where we are going all the way out to the edge of the solar system. We have a telescope, one end of which is sitting inside a warm spacecraft. The other end is looking out into the very cold environment. We heard how cold. It's cold enough to freeze out the atmospheric gases at Earth. We're looking out one end of the very cold environment around the orbit of Pluto. And an ordinary telescope in that situation would go out of focus. But the LORRI telescope will not, and it's because it's made out of silicon carbide. And the LORRI telescope is, in fact, the first telescope of that kind to be flown on a planetary mission. So those are some of the things that are special. What are we going to do? Next slide, please. I'm showing here another image that was, in fact, obtained at Saturn. This is one of Saturn's moons. Pluto won't look at all like this. I think we know that. But I'm showing this picture to give an idea of what LORRI might be able to do. Now, at Pluto, we expect to get images with 6 times more detail. In other words, the number of pixels across the diameter of the object should be about 6 times as great at Pluto as you're seeing here. More than twice as good at Charon. And we also heard about 2 new moons of Pluto. If those moons are as large as they might be, and we really don't know how big those moons are, but if they're as large as they could be, you might get pictures like what you're seeing now of those 2 new moons. So we're ready to, we're about 2 days away now from starting this great adventure. Looking forward to a lot of excitement, a lot of fun. Thank you.
Thank you, Dr. Chang. And that's Dr. Ralph McDuck, Jr., the Pepsi instrument investigator from Johns Hopkins.
Thank you, George. Well, what I want to do is to talk to you about PEPSI. PEPSI stands for Pluto Energetic Particle Spectrometer Science Investigation, which is why we always refer to it as PEPSI. If I could have the first graphic, please. We're going to be using this to actually measure the energetic particle environment that's around the spacecraft. That's due to this interaction that Professor Bagenal was talking about earlier between the solar wind and the atmosphere of Pluto. The instrument itself is sitting on the top deck of the spacecraft, has sort of a fan-shaped field of view, looks in 6 different directions at once, with a small electronics box. It was actually built at APL. It's sort of an evolutionary outgrowth of a similar instrument that's currently on its way to Mercury on NASA's Messenger spacecraft. It was launched here from the Cape back in August of 2004. If I could go ahead and have the next graphic, please. This actually shows the you can see sort of the little semicircle part. That's the sunshade looking back against the high gain antenna, and there's sort of a triangular bracket that the instrument's actually sitting on. So the piece between the triangle and that and up through the semicircle is actually the instrument itself, and you can compare it with the size of one of the technicians that's doing some measurements with it. We actually embarked upon this idea of trying to come up with a miniaturized particle instrument for looking at Pluto's atmosphere back about 1993. And Alan was talking earlier about the fact that there's been quite an investment by NASA about looking at miniaturized instruments. And this one comes in at weighs about 3 pounds, and we use about 2.5 watts of power. And for the same amount of data that we're going to be getting from those similar instruments on other spacecraft such as Voyager and Cassini and Galileo weigh about 10 times as much and use about 10 times as much power. So again, this is a real earmark of the technology that has gone in to making the New Horizons mission possible, because of the need for getting out such a long way in a reasonable amount of time to Pluto, and needing really a small spacecraft to do that. Now, if I could go ahead and have the next slide, please. This is a simplified graphic again of what Fran was talking about earlier. At the top is a sketch showing where that Pluto and Charon on its orbit are. Kind of gives you an idea of this area where the Pluto space is really, Pluto's interaction is really taking over the interaction with the solar wind. But if you go then down to the bottom of the figure, you can kind of see where that we've shrunk that top part down. It gives you a bit of an idea about how far upstream that we think that we may actually see energetic particles. And that translates into perhaps something like about 500,000 miles, or about twice the distance between the Earth and the Moon. And this sort of thing, this sort of interaction is something that we've seen previously at comets. Again, Fran was talking about the fact that in a lot of aspects we think that Pluto may look like a heavy comet. And we've actually made similar kinds of measurements at Jupiter, upstream of Jupiter, looking at material that was originally neutral within the Jupiter system, boiled out, charge exchange with the solar wind, and then was energized so that we actually saw picked up in the solar wind at these remote locations. So it may be that we will actually be able to sense Pluto's atmosphere quite a ways before that we actually get up close and personal with the planet. Again, to mention that the REX experiment is going to be looking at sort of the bottommost part of the atmosphere, the atmospheric interaction with the surface during the occultation measurements. Alan has talked about the ALICE experiment that will be looking at the atmospheric structure somewhat higher up, again also looking at the composition. SWAP will be looking at the solar wind interaction, and then finally PEPSI is going to be looking at the outermost part of that. We'll be looking at both the composition and the energetic particle spectra. We're actually looking at particles that are somewhat more energetic than what you see in the solar wind, from tens of kilovolts up to about 1 million electron volts in energy, and we'll be able to get the composition of those too. Again, a reflection of the kind of composition that we're seeing in Pluto's atmosphere. So it's a long way to go and a long time to wait for us to be able to put these pieces together and to really, with all of these instruments, nail down the escape rate of Pluto's atmosphere and find out what's been going on in the outer solar system over the last 4 billion years, and how that's modified Pluto. But this is what the cutting edge of science is all about, is always making that reach out to the next stage. George?
Thank you, Dr. McGrath. Our next instrument principal investigator will be for SWAP. He is Dr. David McComas from the Southwest Research Institute in San Antonio. Dr. McComas?
Thanks, George. Good afternoon. I'm going to be telling you about the SWAP instrument. SWAP stands for Solar Wind Around Pluto. It was built at Southwest Research Institute in San Antonio. Could I have the first slide, please? In this slide, you'll see that SWAP is the appendage that sticks out the left-hand side of the spacecraft in that figure, fairly large cylindrical object. This is actually a full-scale model of the SWAP instrument from here up to here. We've cut it away so that you can see the inside workings. There are two large doors that flip open that I think you saw earlier in one of the movies from one of the spacecraft tests. Once those are open, this is the largest aperture plasma instrument that will be flown. That's necessary because when you get out to Pluto, the solar wind, this hot gas that's flowing out from the sun, basically the sun's atmosphere, which is escaping into space at all times, it becomes so tenuous that it's about 1,000 times thinner than it is here near Earth. And so it's so very tenuous, you have to have this very large aperture. We have this large cylindrical aperture. And as the spacecraft turns so that the cameras can view Pluto and Charon as we fly by, the solar wind will move around in this aperture and come in from different directions. So the instrument was designed very specifically to be able to handle this sort of environment and the New Horizons spacecraft. The particles come in through a special grid structure, and they get into a region here where they see an electric field between the inner dome and the outer dome, and particles of the right energies are bent precisely through this gap here and down into the bottom part where there are two detectors. We actually have two detectors which make coincidence measurements, so we're absolutely sure to count each and every one of the particles and know exactly what it is that we've got. All of the electronics for the SWAP instrument fit on these three small boards in the bottom here: high voltage power supplies, low voltage, and the computer basically that runs it. So all of that fits in the SWAP instrument, and the SWAP makes measurements of the solar wind and its interaction with Pluto. And if we could see the other slide, please. This is just an example of the sort of thing we might see. This is from a similar instrument which made measurements of the solar wind around the comet Borrelly a number of years ago. And the red and orange line that you see is basically the solar wind energy. Consistent with the solar wind speed, it starts out a little bit below 1,000 electron volts on the left side and on the right side. But in the middle, you can see that it actually drops down significantly below that. That's dropped down because as the spacecraft passed close to Comet Borrelly, it measured solar wind that had been significantly slowed by the addition of a lot of new material. So if the atmosphere of Pluto is boiling off at high rates, as we think it probably is, you should see a similar, very significant slowing of the solar wind, and you should be able to use these same sorts of measurements to make a measurement of the total escape rate at Pluto. George?
Thank you, Dr. McComas. And our final instrument presenter will be Tiffany Finley. She is the Student Dust Counter Project Manager from the University of Colorado at Boulder. Tiffany?
Hi, everyone. Can I get the first slide, please? The Student Dust Counter was developed by students at the University of Colorado at Boulder, and it's the first student instrument on a NASA planetary mission. So far, there have been over 20 students involved in the student team for engineering, testing, and design. And I know our principal investigator, Mihai Harani, is hoping that he's going to get a couple of PhD pieces out of this. It's been a hands-on learning experience for all of the students involved, and it's provided them the opportunity to take ownership of a challenging real-world engineering design. It's been a great source of pride for all of us, and we're hoping that this feeling of accomplishment is going to last us throughout our careers. The next slide, please. The goal of our Student Dust Counter is to map the dust density and particle size distribution in the solar system. We'd like to also estimate the dust production rate at the Kuiper Belt. We're going to be taking the first dust measurements past 18 AU. We're going to hopefully all the way out to about 40 AU where Pluto is in that range. And we're going to be comparing our own dust disk with the dust disks around other stars. And we also would like to thank Alan CERN and the whole team on the New Horizons instrument for allowing us the opportunity to put our student instrument on here. And we're looking forward to Pluto. So thank you.
Thank you, Tiffany. And we'll take questions now. Please give your name once again when the microphone comes to you. Name and affiliation. Craig.
Craig Tavalt with Aviation Week for Tiffany. Is it kind of a get in line deal at the university where there's really a lot of students who'd really like to participate and actively cycle through the project?
When they were first taking resumes, I think, for positions, there were quite a number. There was a lot of interest. Right now, it's kind of just in maintenance mode, and I think over the next 2 years, once we start getting data back, there'll probably be. I haven't talked to Mihai lately, but I'm sure there's going to be a lot of people interested.
Additional questions? All right, hearing none, then that will conclude the briefing.